Okay, the next problem then is problem number 9. It wants us to put it in this form where we have a e to the k times t. So we're going to have to rearrange some things. So let's compare. This is our form we want to get it into, a e to the k t. What we're given is q equals 1/17. And then I'm going to rewrite this. This is 4 to the t. I'm going to make this 4 to the t to the 1/3 because the cube root is really 1/3 power. So I'm just trying to compare here. Let's make it 1/17, 4 to the t over 3. Actually, I'll make it 1/3 times t. That way I can now compare. I've got a. A is 1/17. Now, e to the k here is equal to this. So I can set e to the k equal to 4 to the 1/3. And I can find k, which is what they want. So to do that, I'll change this into log form. So I'll make it natural log base e of 4 to the 1/3 equals k. So just natural log of 4 to the 1/3 in the calculator. Gives you about 0.462. And they also want me to find R and B, where B is the growth factor and R is the growth rate. B is easy. That's just 4 to the. You can enter in 4 to the 1/3 if you want. Now that's right here. I mean, if you have an A, B to the X form, yeah, it's easy to find B. But R is a little harder. What we need to do for that is, once again, compare. And you're going to see A, B to the T. Well, B is 4 to the 1/3, but that's equal to 1 plus R. So B is always 1 plus R. And we can compare to our other formulas, A, 1 plus R over N to the NT. When we're looking at simple one calculation, we're looking at N being 1. So basically we compare, B is always 1 plus R. So if you do 4 to the 1/3, you're getting 1.587. And if you set that equal to 1 plus R, that makes R 0.587 about, and that should be fine. You might need one more decimal place, in which case 0.5874. Okay, the next problem says, which of the following happens to the graph of this? Well, the graph of this we know is exponential growth if A is bigger than 1. So that means that if you plug in 0 for X, you know that whatever A is, you're going to get 1. 2 to the 0th power is just 1. So basically it goes through 1 and it's exponential growth. So as x goes to infinity, y goes to infinity more quickly. As x goes to negative infinity, y goes to 0 more slowly. Both A and B are correct, or D, none of the above. Instead, if one, so we're going to increase A, so we're going to increase our base. Then what happens basically is this thing stays the same, still goes through 0, 1, but it just increases faster. So that's what we want. We want A. As x goes to infinity, y goes to infinity more quickly. Okay, the next problem then, 11. Match functions with their graph. So the first one is just 5 dx. We know what that looks like. That is B. We know that one goes through 0, 1. We can click on this graph to make it bigger. But if you plug in 0 for x, you get 1 for y. And it's just exponential growth because B is bigger than 1. So that's an easy one. The next one, 5 to the negative x. This one we can write as 5 to the negative 1 raised to the x, which we can write as 1 over 5 to the x. So what we have now is our b is between 0 and 1, so we have exponential decay. So we're looking for exponential decay that goes through 0, 1 again, because when you plug in 0 for x, you get 1 for y. So that was E. That's pretty straightforward. This one, we're looking for one that's been shifted down 4 units. So we're looking for one that's been shifted down, that's D. It's been also shifted to the left and then down 4 units, which is what D looks like. And then the next one, negative 5x. This negative sign reflects it over the x-axis. So we're looking for one that's been reflected over the x-axis. That's C. So it's just an exponential growth function that's been reflected over the x-axis. And the last one obviously must be A. And it is because it's shifted 3 units to the right, regular exponential growth. All right, this next problem, problem 12, it wants us to write an exponential function h of t. that's initially worth, so we're going to write this as a b to the t. Now it's initially worth 5,000, so that goes in for a. Our growth factors, we know there's 1/2 left after 15 years, so I'm going to write this because when I plug in 15 in the numerator of this fraction, this turns into 1, and so we're just multiplying by 1/2, and so we'll have half the amount remaining. This happens for whenever you're given a half-life, you can do the same thing. Just make the growth factor 1/2 and put this 15 in the bottom, because that means when you have 15 years go by, you're multiplying this by 1/2, which is exactly what you want. So there's our equation. You can enter that in right here. Or you can also simplify this once again like we do in other problems, where you can make this 1/2 to the 1/15th power, raised to the t, and this is your b. So you can enter it in like this too, and simplify this as a decimal or something. It's up to you, but I think this is the easiest way to enter it in. Just enter in this part right there. Okay, the last problem then says find the exponential function right here, whose graph is shown below. They give us 2 points. They give us the point 0, -3, and they also give us the point 1, -5. So I'm going to use those in this formula. When I plug in the first point, which is good to plug in the first point because there's a 0 for y, I get this, there's a 0 for x. So I get -3 equals a times 2b times 0. And b times 0 is 0. Anything to the 0th power is 1. So that means this whole thing's 1. And a equals -3. Once I have that, now I have -3 times 2b to the x. And I can plug in -5 for y and 1 for x. And I can solve for b. So I'm going to divide both sides by -3. And now I have 2b equals 5 over 3 if I rearrange. 2b equals 5 over 3. And then I can make this log base 2 of 5 over 3 equals b to change from exponential form into log form, which is something we're going to have to practice some more. So this is, if you do your calculator, 0.736, we can do 0.737 maybe. So 0.73, I'm sorry, that's b, 0.737 for b. And then to find, we already found a was -3.